Okay, so, all right. We're getting to the end of this part 2 of Unit 1. Just as a recollection, I'm going to just remind you what we did in part 1. Remember in part 1, we looked at atoms. We looked at the way the atoms are built. We looked at the protons and the neutrons in the nucleus and the electrons that are in orbit. We looked at Bohr and Lewis diagrams so we could have an understanding on how the electrons are. And the Lewis diagrams were the important ones. And we're getting pretty good at Lewis diagrams. We know that group 1 has 1 dot and group 2 has 2 dots, 3 dots, 4 dots, 5, 6, and 7 dots as we work our way across the periodic table. So then in part 2, we asked the question, what happens when the atoms get together to form bonds? And up to this point, we talked about ionic bonds at the beginning, where there was a complete transfer of the electrons. We learned how to name those ionic compounds, things like sodium chloride or calcium carbonate. We did a quiz on that. And then we talked about bonding. And we drew some single bonds and double bonds and triple bonds. We talked about molecular compounds. When 2 non-metals bond together, we put the lines to represent those sharing electrons. And we actually completed that. We've come to the end. We are now getting pretty good at drawing some Lewis structures, and we even made some molecular models. To finish off, we need to look a little closer at this bonding, all right? And everybody seems to be writing right now, which is what you guys do, you write. And I want you to listen just for a little bit, all right? So up to this point, we have talked about molecular substances, all right? And we drew some Lewis diagrams of some molecular substances. Let me just give you an example on the page here. You don't need to write this down, but if I'm talking about something like NH3, we hopefully can come up with a structure that looks like this. I don't think that's too outrageous. We know that nitrogen is in group 5. It needs 3 more electrons so it can form 3 bonds. It has a lone pair. It's happy, and the hydrogens are happy with 2. And that's a good molecule. There's nothing wrong with it. And we know what all these symbols represent. 2 electrons, 2 electrons, 2 electrons, and 2 electrons. What we want to learn today is still dealing with molecules. We're still looking at molecules, but now we're going to look very closely at what's happening in that shared pair of electrons. What happens when we say that the electrons are being shared? Because in grade 10, we would have had you draw a similar thing. We'd say, oh, look at the atoms are getting together so nicely. They're sharing their electrons. Isn't it lovely? Well, it turns out that it really has nothing to do with sharing. And so we want to look in closer detail about what is going on inside those bonds. So that's what today's lesson is about. We know how to draw a Lewis diagram. We know how to draw single, double, and triple bonds. We know how to deal with a lone pair. We're now asking the question, what's going on in that shared pair? It doesn't change the way we draw the pictures, but it changes the way we interpret these pictures. It gives us a little more meaning. Okay. So the first thing that we need to learn about is a special number that is found on our periodic table. And you guys who are writing away can continue to write away. And you are going to need your periodic table because these numbers are found on them. So like I set that up like at about 20 after. Did you get it and run over and print? And the other one? And you did it like in that last 10 minutes of class, or you did it the other day? You didn't print it off yet. Yeah, because I didn't put it up till late. I apologize. I got to like 20 after and I'm like, oh no, I forgot to put up today's work. So we will need our periodic tables. So once you're finished writing that slide, or if you're going ahead, stop for a minute and get your periodic table out. Now this table here is a table that existed on an old periodic table that we used to purchase and then we would laminate it, and we'd sell it to the students for like 25 cents a piece or something like that. Yeah, they were really good periodic tables, actually. I sometimes have former students who have gone on to university have come back and said, hey, can we buy a few more of those? Because like if you have to go to the bookstore at the university, they're charging like $10 for a good periodic table. So yeah, it used to be a pretty good table. But then the company that we were buying it from, they stopped selling them. So I didn't like the other ones. So that's when I went online and found various tables and kind of built my own. Now, this table was the table of electronegativities, kind of a handy little table. It had group 1 and group 2, and then we jumped across the transition metals, group 13, 14, 15, 16, 17. Now, on our table, the electronegativity numbers are hidden in the boxes, which is why I want you to have your periodic table out so you can track down the electronegativity. If we take a look at the legend, the hydrogen in the middle there, that's our legend, you should be able to track down the electronegativity number. Can you find it? Looking in the legend there, where the electronegativity is, that little number right there. Can you find it? So you'll notice, and if I ask you to find it, like what's the electronegativity of hydrogen? What do you have? Electronegativity of hydrogen. Yep. 2.2. Did you actually look at the chart? As opposed to like that chart right there in front of us? Oh, that's exciting. All right. 2.2 is correct. And you can see here, and this is just for me to look at, but you'll notice these numbers are actually a little different than the numbers on your periodic table. Notice for fluorine, what value does your table have for the electronegativity for fluorine? What's that? 3.96, where on this table, it's rounded to 4, all right? Don't worry about that. When we use the numbers, we're going to use this table, all right? And you can see that every one of those atoms, except some of the noble gases, they won't have them, but every one of those atoms will have an electronegativity. So what is electronegativity? Well, it's a number that's mathematically created by scientists. You do not need to worry about where the number comes from, but it's a number that represents the atom's attraction for the shared electrons in a bond, all right? The higher the electronegativity, the stronger the attraction for the electrons. We've taught you in past science classes, and even in this chemistry class, that when we have a molecule, we say that they need to share their electrons, that it's a nice little, agreement. Let's share electrons. You'll notice in this statement, it says that we have numbers that describe how strong an atom pulls on electrons. So really, when we form a bond, it's not sharing. It's really more of a tug of war. They get together, kind of like pulling on each other's noses, right? My silly example. And when they get together, they're pulling constantly because of their nucleus on those electrons. And some atoms pull stronger than other atoms. Which atom is the strongest of the pullers when it comes to the electronegativity? Which element pulls the strongest? What do you got? How did you know that? It has the biggest number. Notice on my chart, it's a 4. It has the biggest number. Notice what happens to the electronegativity, its ability to pull, as you move down a group. So maybe say starting with fluorine, you could take a look at your chart right now, Stephanie, you could do that. And you could look down the group and see those numbers. What happens to the numbers as you move down? They get smaller. So as you move down the group, the elements get weaker at pulling on the electrons. Okay? What happens if you move towards the left of the periodic table, towards the metal side? What happens to the electronegativity? Alexis? It decreases. I couldn't hear you. That's my fault. It decreases, correct. So take a look at your chart. Which atom is absolutely the most pathetic atom when it comes to pulling on electrons? Which atom is the weakest of all of the atoms when it comes to pulling on electrons when they're trying to share? Alexis, did you find it? Francium, excellent. So francium is the wimp of all of the elements when it comes to sharing electrons, And fluorine is the muscle-bound, I don't know, the muscle guy that kicks sand in people's faces at the beach? No? You? All right. So that's what that number represents, how strong it pulls. All right. Man, I'm hearing sounds everywhere. You don't have to write these little two things down. Write those little two things down. We just discussed it. We'll write it down. There's bings and sounds and I know. Non-metals have higher ENs than metals. Fluorine has the highest EN, the highest electronegativity. And the term electronegativity is kind of a made-up word. It contains electron, it contains negative, and it has to do with these electrons being moved in a certain, by being pulled. Has to do with these electrons being pulled. Okay, there's two little tiny bullets there. I don't know where we're writing. Everybody's writing ahead. Let me know if I'm going too fast. Okay, so when a bond is formed, we need to see which of the two elements is the strongest. And we want to know how much stronger the one is than the other. So what we do is we simply mathematically subtract them. The symbol delta, it's a triangle. Delta in physics and math and science means a difference in. It's a subtraction. All right, so if you've taken physics with Mr. Petrus, you know that V is equal to delta D over delta T. He might have written it that way. He might have written it as D over T, but delta D over delta T. It means you subtract the distances and subtract the times. In this case, the delta EN is the difference between them. So we need to subtract to see who's the strongest. Do we have two of the strongest pulling on the electrons? Do we have weaker ones, or do we have a strong one versus a weak one? Now, when we do this math, it gives us a number, and that allows us to tell us what type of bond it is. And that's why this is called types of bonds. So let's define some of this stuff. Oh, okay, I'm cheating ahead. So as scientists, we have, not me, much smarter scientists, have decided that if you subtract the two electronegativities of the two atoms, and you get a number that's between 0 and 0.2, all right? And you know what? We've got to make sure we have a distinction here. This means that our values are between 0 and 0.2. We're not talking about a subtraction here. This is not, right, a subtraction. We'll do the math in a moment. What I'm defining is a range of numbers that when we subtract the two numbers and we get an answer, and that answer is between the numbers 0 and 0.2, we say that we have a non-polar bond, all right? It means that the electrons have not shifted over very far, all right? And you know what? If I were to redo this lesson, I would reorganize this. But bear with me, and I'll show you what the opposite is, what a polar bond is. Actually, you know what I'm going to do? Yeah, I'm going to change the order of this. I'm going to define what a polar bond is, and then we'll do examples of both together. All right, I'm going to change things up a little bit here. Do we have that written down? Okay, excellent. So I was going to do examples, but now I'm actually going to jump ahead and define what a polar covalent bond is. And then we will look at both examples. Again, this doesn't mean subtraction. This means between 0.2 and 1.7. See what I mean? Maybe I should have an arrow from 0.2 up to 1.7. Right. Treat 0.2 as the polar starting point. So it's up to 0.2 for the previous one. This one is at 0.2. But you know what? I don't know of any combination on the periodic table that has an answer exactly equal to 0.2, so you don't have to worry about it. Okay. Okay? But I understand what you're saying. What I really just want to state to you is that I'm not subtracting here yet. We will do some subtraction in a moment. So polar covalent bonds are formed when two nonmetal atoms have different electronegativities, and they share electrons to form a covalent bond. If the electronegativity difference is in this range, then we say that they're unequally shared. The electrons are not shared equally. The bonding electrons spend more time closer to the atom with the higher electronegativity. I'm going to put this on a picture and make it nice and clear for you. All right? This creates regions of partial charge called dipoles. And that last statement to you is probably a whole bunch of blah, 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 blah. And I need a picture to help you understand that. So we're going to do some examples and we're going to explain the difference. Don't get too far ahead, example writers, because I'm changing things. What are you doing here? Oh, you're still writing the same part. Good, good. Don't get past this, because I'm now going to go to a different note program, and I'm going completely off script. I'm going to combine the second part of this lesson all into one, and then I'll just let you work on various stuff to finish things off, because there's no need for it to be separate. Okay? Did you go too far? Okay, good. We do this in the 3U, and I do it completely different than this. This, to me, is a little clunky the way we're doing this. So I'm going to define one last thing. I was going to do examples. I've changed my mind one more time. I'm going to write something else down. Could you find a situation that has well, you see, you could, and we haven't done any calculations, so I can't actually ask you to find a calculation, but what if we have a delta En that's bigger than 1.7? What kind of bond do we call that? Well, we have a name for it. What's that? Extrapolar, or like really super duper polar? And you're right. It is. It is extrapolar. It is really super duper polar. But we have a name for that, and we've actually already encountered it. And that's where this second part of the note was to come in, but I'm going to add it right here. So I'm going to go to this note program because I want to keep making the movie for Mark. The third type of bonding we already saw. This is called, and why doesn't my pen work? This is called ionic bonding. If the delta En is equal to 1.7 up to 4.0. That's the greatest difference that we can have. Then we have an ionic bond. If the delta En is so great the pair of electrons is considered to be completely transferred to the element with the larger En. We say that if the delta En is so big that it's not just unequal sharing anymore, it's a complete takeover of the electron. Completely transferred. Okay? Look good so far? I want to move this piece of paper. I can't remember how to do that. Extend the page. Extend the page. Okay. One last thing before we do the examples. The bonding continuum. I spelled that wrong. There's not two U's in continuum, is there? Anyway. I killed it. How do I spell it? Did you find it? Bonding continuum? Oh, I did. It was correct? Oh, bummer. All right. Continuum. We've talked so far today about this unequal sharing and how it depends on how strong the atom is at pulling on electrons. What that means is, in the past, you've learned about bonding and you've always thought about it as being ionic, which is, didn't we do this yesterday? Ionic? What two elements do we need for ionic? A metal and a nonmetal, or molecular. You remember? Molecular? Two nonmetals, right? We've always said it's either ionic or molecular. Those are the only two choices. But in actual fact, it's not that cut and dry. There's degrees of sharing, and that's what the bonding continuum is. If we calculate this delta En, and I'm going to show you how to calculate it in a moment, we actually have this spread of sharing. If the delta En is from 0 to 0.2, we say that's practically equal sharing. We say that it's practically equal sharing. And we call this non-polar. Non-polar. It's a non-polar bond. Yep. No, not yet. Are you dying? Does it? But this is the most important, most exciting part of my lesson. Give me another 4 minutes. From 0 up to 1.7, we say that it is unequal sharing. and we call it a polar covalent bond. Polar covalent bond. And if we have it from 1.7 all the way up to 4.0, we say that it is so unequal, we say that it's a transfer. And if it's a transfer of the electron, what type of bond did we call that? We've already seen it. It's ionic. Ionic. Yep. Because you actually, I picked 4.0 because that's our biggest number of the fluorine. But if you subtract, you never actually get to 4.0. You actually have to subtract one away. So if you subtract the smallest from the biggest, you get 3.3. Don't worry about it. There's just no number for 4.0. But I've always just memorized it as being 4.0, the biggest possible number you can have. This is the most important part, which is why I have you stay. Let's do a couple of examples here. My example to begin with is going to be the bond between a P, I'm not able to write on it, a P and an H. The bond between a phosphorus and a hydrogen. So here's what we do. Delta En equals. What's the electronegativity for phosphorus? Now I need you to find it on the chart and tell me what the number is. Yep, what do you got? 2.19? 2.19. What's the electronegativity for hydrogen? Yep, 2.2. Now we need calculators or perhaps phones, which I don't like you using as a calculator. But anyway, could somebody do that calculation for me? Tell me what you get. Yep. Never mind. That's exciting. What do you got? 0.17? No. 2.19 minus 2.2. 2.19 minus 2.2. Felicia, what do you got there? Negative 0.01. We actually don't care about the negative, so we drop it. In mathematics, when you get rid of a negative, what we call it is the absolute value. Have you ever learned that before, where you say, let's forget about the negative, let's just take the value of it? So they put those lines beside it. Have you ever seen that before? Anyway, that's what that means. Don't worry about the negative. Now notice, 0.01, it's in this region. We say then that this is a non-polar bond. All right? HCl. Delta En equals 2.2. I think we've just seen it. Cl. What do you got? 3.16? 3.16. And ignore the negative. It gets you 1. Yep. 0.96. Notice the chlorine is stronger than the hydrogen. In a moment, I'm going to teach you what that means, and we're going to talk about what a dipole is in a moment. All right? I'm going to do that just in a moment. But notice it's under here because this number is in this range. Therefore, we say it is a polar bond. Okay? Now, I'm not going to, my next example, and once I'm done this example, you can go ahead and get your drink of water, is going to be NaCl. Now, notice I didn't put a bond in there. Because what type of compound is that? Just by looking at the atoms, what type of a compound is that? Ionic. Let's see if it mathematically works out. Delta En. I don't know what sodium's value is. What's that? 0.93. 0.93 minus, we've seen this number, 3.16. And what's the delta En for that? Calculating away. What do you got? 2.23. 2.23. Notice that the En is in that range. Therefore, we say it is ionic. Okay? Alexis, you can go and get your drink of water here in a moment. Or actually, go ahead and get it right now. Does everybody kind of understand what we mean by this continuum? Now, notice we could have a number of like 0.13. It's kind of polar, but it's not polar yet. We still say that it's nonpolar. We could have a number of 1.62, and we could say, whoa, that's really polar. It's not quite ionic, though. It's not high enough. And we could then have into the ionic region, and we could have ionic. All right? Now, I want to look at HCl a little closer. What does it mean to be polar? Extending the page. Like an infinite whiteboard. So let's look at HCl a little closer. HCl. And you can make it larger. Put it underneath. And you need to flip your page, I think. Your page looks full. It is. It's good. It's huge. It's awesome. You've got to make it good. So here's what we have. Here's our regular electrons. And there's a pair of electrons in here. And the delta En is polar. And you'll notice that chlorine has a greater pull on the electrons. So like I said a minute ago, it's not that they're sharing, it's a tug of war. And who's winning the tug of war for these two electrons? Chlorine is. What that does is, in this pair of electrons, which you might imagine to exist right in the middle, because that's what sharing would mean, actually exists closer to the chlorine, because it pulls harder. We draw an arrow to represent what direction the electrons go. So we put an arrow along the bond pointing in the direction in which the electrons shift. So it points towards the one with the highest number. We put a little plus on the back end of this, and I'll explain why we put a little plus on the back end of that thing. What does that do? That actually makes the chlorine side of the molecule a little more negative than the hydrogen side, because this pair of electrons that we thought existed right in the middle actually exists closer to the chlorine. That gives the chlorine a tiny bit of a negative charge. Now, it's not like a full-on charge. It's just a little bit of a charge. We have a special symbol for that. That symbol is a delta, which is a lowercase delta with a negative sign. Okay, now we're getting into some good stuff here. Saying a lot of things, but it's okay. This, yeah, that's a delta. It's a Greek letter, D. This is the capital delta, the triangle, just like a capital D. See? Capital D, capital delta. This is the Greek version of the letter D. Little d, that's a letter D, it's a little one, right? And then a little delta, it's like the number 8 that doesn't quite ever get finished. It's like I get lazy and say, I don't want to finish that number 8. I'm just going to stop it right there. See how I kind of made that? And see how it kind of looks like a D, except it's like a fancy D? That's the Greek delta. Now, what that simply means is a little bit. It needs a little bit. So this end is a little bit negative, and this end is a little bit positive. And it's because the electrons have moved a little bit. Okay? Now, what is this? It's a magnet. Very good, Amy. Nice job. What's special about a magnet? It can pull and it can the other one. She means push. Because if I bring another magnet to it, it can pull or it can push. Very good, Amy. Why is it that a magnet can pull and push? Why can it do both? What's special about a magnet that allows it to pull on one end and push on the other end? What do we call these ends of a magnet? Don't rely on Amy. What do we call the ends of a magnet? What do we call that from years ago when you learned maybe some science and some grade? What do we call those ends? You know?
I didn't learn good science.
He didn't learn good science. That's good. You were busy learning good English at the time, I assume.
No.
Okay. No? Nothing? What do we call the ends of the Earth in which the axis rotates around? What do we call those ends of the Earth? The equator? Let's go with the other end. The poles! Yay! They're the poles because they're on the ends of the Earth, the end of where it rotates. What do we call the ends of a magnet? The poles! Nice, right? Because they got ends on the end of them. And how many poles are there in a magnet? 2. And when we have 2 poles in something, we put the words to and poles together as one word to describe this thing. We call it a dipole because it has 2 distinct ends, and it can push and it can pull, right? If you take a look at our molecule that we just drew here, notice now that it's got a distinct slightly negative end and a distinct slightly positive end. It actually behaves a lot like a little magnet, except a magnet has magnetic poles. This has charges on the end. That arrow and these charges represent what we call a dipole. Okay? Now, I just did a lot of talking there, and we're going to go back and do some simple examples. I'm going to do some more examples with you. But I just want to now go back to our PowerPoint for a moment. And that's because I went through this right here at the note. You don't have to write this. Notice it said, if we have between 0.2 and 1.7, we say that it's unequally shared. What did that do? It shifted the electrons over. If we do that, we create regions of charge. That's those little deltas. One side is negative and one side is positive. And because we have one side being negative and one side being positive, we call it a dipole. And that's where all these big words come from. Okay? Let's do more examples. So I'm going to just slide this guy down here. I'm going to extend, and I'm going to move up here. And we'll call this example, right? And we're going to draw the Lewis diagram. Okay? We're going to calculate the delta En and state the bond type. Okay? And we're going to draw on the dipole when necessary, right? If it has one. And the first one I'm going to do is F2. All right? And then we're going to do an HBr. Oh, and I already started drawing it out. I didn't want to do that. I just wanted to write HBr, but I'm busy thinking and writing at the same time. And then we will move down and we'll do 2 more. Okay, F2. We've drawn many Lewis diagrams. How many outer electrons does fluorine have? 7. And they're both going to have 7. How many bonds does fluorine normally have? 1. So put them together and draw your Lewis structure. Have a pencil so that if you make a mistake, you can fix it. And if you need a pencil, there's pencils right here. I got lots of extra pencils. Could somebody tell me how to draw this? Remember, we say lone pairs and single bond and double bond and all that type of stuff. Okay, I'm going to call on Amy one more time, and then she's going to have a rest. What do you have, Amy? Single bond? All right. Calculate the delta En. I put the delta En right underneath the bond I want to study. What are my numbers? Conrad? Yeah, or using our table, it would be 3.96, 89, 98, 3.98. It doesn't matter. We can do 4.0. That's just the 2 digits, right? It doesn't make any difference. I'll do 4.0 minus 4.0. If you did 3.98, it doesn't make any difference. What is the delta En? What's the value? 0. So what type of bond do we call it? If the delta En is 0, out of the 3 types that we have, what do we call that? Yep, nonpolar. Nonpolar, which means there is no dipole. I'm just going to write that in. Therefore, no dipole, which means we don't have to put any arrows on this picture. The sharing is even. HBr. I already kind of gave it away. What do I need to do to finish my picture? How many? Bromine. 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 It's over here.
Oh.
How many outer electrons? There's not -1 outer electrons.
7.
There's 7.
7.
So there's the 1, and we need 3 lone pairs, just like a fluorine, right? Looks just like a fluorine. Delta En. I've been using them a lot over the last few days, so I've memorized that it's 2.2. And what is the bromine? 2.96? 2.96 delta En. I'm not doing that math in my, actually I could do that math in my head. 0.76. 0.76. 0.76. Therefore, what type of bond is this? 0.76? What is it? It's on the other side of the page. It is polar. If it's polar, it means there has been a shift. Is there a dipole in this? Yes. If it's polar, there's a dipole. Yes, there's a dipole. Which direction, towards which atom, will I point the arrow? Yep. Why did you say bromine? En. The electronegativity is greater. The arrow goes towards the bromine. If I were to put my slightly negative, what atom does it sit closest to? Yep. The bromine, because that's where the electrons go, and electrons are negative, right? Slightly negative, slightly positive. Okay? Let's do one more. Extend the page. Oh, what's going on here? Cancel. Get out of the way. Cancel. And my example is going to be H2O. Good old water. Sorry? Good old water? Water? I did that on purpose. I don't say, oh, is that?
I don't know. You made up one.
Water is good for me as well. It doesn't have to be water. Water is okay. Water. Like Toronto versus Toronto. All right. Anyway, let's draw this up so that I can give you your work to work on. Could somebody tell me how to draw this? So oxygen, how many lines, how many lone pairs? What do you got, Jess? Hydrogen? Single bond? Oxygen? Two lone pairs, single bond, hydrogen. Notice that their bonds are the same, oxygen and hydrogen. So we just need to look at the electronegativity between oxygen and hydrogen. We're looking at the bonds. So delta En, 2.2, I got that one. 3.44? 3.44, just take what you find on the periodic table. 3.4 would be fine. What do we get when we subtract those? Yep.
0 decimal 2.
Nope. 1.24. 1.24. What kind of bond is this? What kind of bond is this? Yep. Is it? What's our range? What do we? Yeah, it's polar. It's 0.2 to 1.7. Polar. Is there a dipole? Yep. Yes. There's a dipole. There's actually two dipoles in this, one for each bond. Which atom do I point my arrow to? Alexis? Oxygen. And I'm actually going to have one go this way and this way. Where am I putting the delta negative? Which atom is it close to? Yep. Oxygen. Delta negative. And delta positive. And delta positive. It has two of them. Okay. Now I'm going to stop my lesson there, and I'm going to guide you to the worksheets to work on. All right. But before I do that, I want to show you one thing. And before I do that, I'm going to stop my recording.